So what I'm going to do today is to sort of recapitulate our discussion on this ultracold bosons a little bit, because it fits with the other content of the lecture, and then talk about several possible systems or models that you can emulate in optical lattice using this cold atom setup. And I have two particular things in mind. One which I'm going to cover in details, and the other one is probably going to be the subject of the last lecture.
One day on our website, we will have a separate tab for this, and then
Hello.
By the way, Avinash is working on flash web application, which is very advanced. What we are using now is simple,
Okay. So
yes,
and then we don't.
Let me try to sort of get into the
admin interface from this.
next part, which is, so first the recapitulation. So as I said that, this cold atoms length to of the order of 10 to the power -7 kelvins, and now it has gone to a nanokelvin or so, and that's by far the coldest temperatures that you can think of. And in this kind of settings where you have this cold atoms, what you do is that you essentially try to put atoms in this temperature, and since they are very, very cold, they are well below their post-condensate temperature. These atoms are bosonic, and so you get a BEC. The interesting thing about this is, of course, that to measure this temperature, you take help of statistical mechanics. And as we discussed in the last class, the width of the peak of this central distribution, this is the momentum distribution of the atoms. So the peak width of this central peak, in this momentum distribution, is essentially gives you an idea about the temperature. Okay. Because it's really, really cold, you cannot just stick in a thermometer out there because it's going to heat up all the system. And of course, so we discussed these cooling techniques. So first we saw how using this Doppler shift, we can create a cold bunch of atoms, and this is called optical molasses. And then we put that molasses in a trap, and this trap is then selectively lowered so that the high energy atoms, which resides at the top of the trap, goes out, and what is left has a much lower temperature. And this is what you use. It's called evaporative cooling. And the reason it's called evaporative cooling is that it's exactly the same mechanism by which your coffee gets cold in a winter morning. This technique of evaporation, and this is how they reach the critical temperature of a BEC. So after you have created this Bose-Einstein condensate, what one does to emulate cold atoms is to put in a lattice. Now this lattice is done by putting counter-propagating lasers, which forms a standing wave of light. And these atoms have a polarizability, and therefore, because it has an electric field due to this light, essentially it sees a potential which is its polarizability alpha times mod E square. Now, this quantity alpha is taken to be positive. This, of course, depends on what frequency of laser you choose and what the characteristic frequency of the atom is, and all details are taken into account to make alpha to be positive. And this means that the atoms would like to sit at the bottom of the potential generated by the laser. So clearly here there is a competition. In the absence of this lattice, optical lattice, the atoms are going to be all delocalized in space because it typically occupies the k equal to 0 momentum state, which means totally delocalized in real space. Whereas for a very deep lattice, it's going to go and sit at the bottom of the lattice potentials. So essentially, this competition is what gives rise to some very interesting physics. And moreover, you can now do block theory with bosons, which you have done in condensed matter in context of standard physics. Now, here is a comparative thing about these optical lattices and crystals that you typically see in solids. So first of all, solid crystals are given to you by nature, and they are not prepared. Well, now probably we are getting there, but the point is, in general, that's the case. But optical lattices are fully controllable. You can make this such that there are no defects, and these lattices do not vibrate, in the standard sense of vibration of solid state lattice. So lattice spacings are in micrometers, and these are much larger spacing compared to lattice spacings in angstroms in solid state crystals. So the trapped atom mass is, so these atoms are heavy, so they are between 10 to 100 atomic mass units. So for example, if you take rubidium atoms, it's 87 AMU, okay, because its mass number is 87. And for an electron, it's like 1 over 2000 AMU, essentially. So it's really, really light. The most important difference is that this temperature of this, in which you can maintain this lattice, is of the order of nanokelvin, and here it's of the order of 100 Kelvin. Okay. So the point is that this is a perfect platform for realizing physics of interacting quantum matter using bosons. Okay. And we discussed this experiment where you prepare basically your system in a BEC, okay, by this called creating this evaporative cooling and optical molasses and all that stuff, and then you ramp up the optical lattice potential to a fixed value very slowly. So 80 milliseconds is a large chunk of time when it comes to system timescales, and then you let the system basically equilibrate for about 20 milliseconds, drop everything, and then measure whatever is there in the trap. Now the point here is the following, that if, say for example, this ramp, this potential, which is this V naught or V max, whatever you call it, is small, okay, or zero for that matter, then here all the atoms are in BEC, okay, so they are sitting at roughly k equal to 0. After you drop the trap, these atoms expand, and this is a free flight because you have dropped everything. You have dropped the lattice, you have dropped the trap, everything. So this atom is these atoms are now a cloud which simply expands, and during this free flight, the trajectory of the atom is essentially determined by its initial velocity, or in other words, its initial momentum. So if you take the projection of this atom on a 2D screen, the position of the atom on the screen is a reflection of the velocity of the atom before you drop the trap. Okay, because its position. So if the screen is right here and the atoms come and hits the screen somewhere, the point at which it is going to hit the screen is basically determined by its initial starting velocity, because it's just a free motion. Okay? Gravity is negligible, so it's basically a free flight. So in that way, the position distribution on the top of the screen is same as the momentum distribution of these atoms, and therefore, if you have zero potential, it's in a BEC state, which means it's at k equal to 0, okay, and it occupies the central part of that screen. As we increase the lattice, the central peak stills and other peaks appear, because now you have a lattice, so there are reciprocal lattice vectors, and the atoms could be at those vectors. However, at around 14 times the recoil energy, ER, which is given by this, it turns out that the central peak dies. And as a result, what happens is that the atom is no longer in a BEC state. And for large V naught, you see that the atoms are completely delocalized on the screen, which means they are completely delocalized in momentum space within the trap. Okay, its momentums are, so the momentum distribution is completely diffuse, which means that it's very well localized in real space within the trap. So you go from a very yeah.
Hello.
Yes.
So at B naught is the magnitude of the trap now. B, because
that's
we are
right.
writing B is
That's
equal to
actually,
B
I'm
naught.
sorry for this difference in notation. This V naught is actually V max. Okay, so the maximum height of the trap that you have.
Okay, sir.
Okay. So in doing this, what we see is that we pass from a state which is very well delocalized in real space within the trap to very well localized within the trap, and so there is clearly a transition out here, and people have looked into this thing in more details. Okay, so let me skip this. We have already seen this, and what people have seen is that a model Hamiltonian which captures this physics is indeed the Bose-Hubbard model, where the bosons can hop between different sides of the trap, and it's enough to consider just the nearest neighbor hopping. And then there is an interaction between these two, and this interaction is repulsive. So these bosons are typically 87 rubidium atoms, which are neutral atoms, and their interaction is, it's not Coulomb, it's short-range interaction. The point is that this short-range interaction is well approximated by just on-site interaction. Okay, so the model assumes that the bosons interact if and only if they are on the same site. And then, of course, you put in a chemical potential for calculation. And this model essentially leads to, a Bose-Hubbard. So this is the Bose-Hubbard model, which successfully explains the transition from a Mott state, where all the bosons are localized, to a superfluid states where they are delocalized. Okay. So we have discussed this. So this is just a recapitulation. And now I'm going to come to the main topic of this of today's lecture, which is essentially breaking translational invariance of these bosons. Okay. But before that, any questions regarding anything on these ultra-cold atoms which I have discussed so far? Because this part is the basic, which is going to be important as I go on. Any questions?
Hello, sir.
Yes.
Sir, ultracold physics we model like now Bose-Hubbard model recently we have seen.
Yeah.
So can this ultracold physics can be seen in the fermionic model, fermionic Hubbard model? Can you describe?
Yes. So the point is that I'm not going to discuss this in this talk because there is no time. But the point is the following. So just like the bosons, people have also tried to get ultra-cold fermions. But the point is it's much more difficult to cool these fermions and achieve a temperature which is below their coherence temperature, where you can form these quantum objects with these fermions. Okay. Typically, there is some success, but the physics of it is very complicated. The reason is that, for the bosons, the starting state is very simple. It's just if all the bosons in K equal to 0 state. On the other hand, for these fermions, as you know, there is a Fermi surface. So all momenta up to some kf is occupied. Okay, and then the problem with this is that typical measurement of this invokes either real space measurement, which I'm going to discuss today, or momentum distribution measurement, which I have discussed in the last class. Now, with this momentum distribution measurement, there is a problem. The problem is that it's not like having a central peak in the momentum distribution. You'll have many momenta which is essentially occupied if you do a pre-flight of these fermions, and that essentially complicates matters quite a bit. Okay, the pictures are not that simple. And the second thing is that, of course, there is this experimental problem that it's much more harder to cool fermions compared to bosons for several reasons, which I'm not going to get into. There is a very nice review article by Emmanuel Bloch. It's in 2011 or 12, something like that. I'm going to send you the reference at some point. But that discusses these different aspects of cooling fermions and green stuff. Okay.
Okay, sir. Thank you so much.
Sure.
Hello.
Yeah.
So my question is regarding the experimental technique actually. So like you are trapping the atoms in the optical lattice, and after forming the Bose-Einstein condensate.
No. I'm trapping it in a trap which could either be optical or magnetic, and then I'm putting a lattice on top of it.
Okay. So like for evaporative cooling, we are using the magnetic traps.
Yeah, we could also use optical trap. That's also possible.
So like because the optical trap, they will add a spin degree of freedom in the system, but magnetic trap, we don't have that freedom. So my question is,
no, actually, see, most of these experiments are given with 87 rubidium atoms, which by itself in a state of F equal to 1, I'm going to come to that. Okay, so it's all spin polarized.
Okay, sir. So my question is like those magnetic traps is formed by the anti-Helmholtz coil or like something else, because that the minima, the sharp minima.
Yeah, that's right.
Anti-Helmholtz.
Sure. Yeah.
So my question is like those traps is from anti-Helmholtz coil or something else we are using here? Like,
no, so okay, I don't know the details of this very well, but the point is that what they do is that, you know, they probably, okay, the last time I remember reading this was very long back, but most likely in those times there is this anti-Helmholtz coil which was doing the thing. But okay, I haven't looked up it in a long time. So all I can say is that, you know, you can also do this, but I'll also try. There is a book by C.J. Pethick, which is on these details of trapping ions and cold atoms and stuff like that. That has all the details about how experimentally you put these things on a trap.
Yes. Thank you, sir.
Okay.
Sir,
Yeah.
hello. Yeah, sir. So my question is it possible to have a vibrating optical lattice?
Yes, of course, it's possible to have a vibrating optical lattice. So what you do is that you slightly mismatch the frequency between the two counter-propagating lasers, so that you have a tiny bit frequency, which is the vibration of this lattice. But typically, for static purposes and for getting the phases and stuff like that, you take non-vibrating ones. Okay.
Right. So one can, in principle, emulate some phonon boson interaction kind of thing if you want.
Oh, those. So yes, and in principle, but those are experimentally much more complicated. You see, the problem is that you are doing this with bosons and not with fermions. Okay, so if you have superconductivity in mind because of electron-phonon interaction, which is the first thing that comes to mind, that's not the thing here.
Yeah,
Okay, because everything is boson. And also there is this thing that if you want interaction between two different species of bosons, you know, that can be done by putting in by taking spinor bosons, which people have done.
So the spinor bosons.
Yeah, so if you have two states which the boson can occupy, you know, and then it's like having two species of bosons, and then you can think of interaction between them and stuff like that. It's typically called two species bosonic systems, which people have looked into. Okay. Okay. Any other questions? Okay. If not, let me just get into this topic of breaking translational invariance with this optical lattice. So there are several theoretical routes of breaking translational symmetry, but first let me tell you why we want to break translational symmetry. So you see that when we realize an Bose-Einstein condensate, we already break a symmetry called the U1 gauge symmetry, you know, which is what happens when you form Bose-Einstein condensate, and the presence of a definite phase of these bosons, you know, is a consequence of breaking of this symmetry. So the ground state picks up one possible phase from many possibilities. Okay, and that gives you this Bose-Einstein condensate. But there are also another kind of symmetry that you can think of breaking, and that's basically translational symmetry. Because we know that in standard condensed matter systems, we can have translational broken symmetry states such as charge density waves and spin density waves. And also there are several spin systems where this translational breaking symmetry breaking takes place, such as antiferromagnet. So since it's all about emulation of condensed matter system, this is certainly symmetry breaking that comes to mind. And theorists have several ways of doing this. In fact, the first thing that one can think of is that you can take two or more species of ultracold bosons. Okay, these are two states of the atoms, and you can selectively put bosons in those states. And essentially, so there could be an on-site interaction between these bosons and an interspecies interaction. And this is the interaction between two bosonic species that I was talking about a minute back. And essentially, if you take this and look at the Mott phases of this, because there are two of this stuff here now, you could have an antiferromagnetic state, which means that you have species A sitting on one sublattice and species B sitting on the second sublattice. So it's like an up-down system. Okay, or you can have a ferromagnetic state where it's only species A which is sitting on every sublattice. Or more interestingly, you could also have an XY phase where there is a coherent superposition between species A and species B on each side. Okay, so this antiferromagnet certainly breaks translational symmetry, and this is one way of getting a translational symmetry broken state. Okay. The other thing to do, of course, and this is again theoretical, is to have a translational symmetry broken state by putting in a next nearest interaction between the bosons. So we already saw that there is some, in the Hubbard model, there is some on-site interaction, which tells you that if you put more than one bosons on a given site, you are going to have a cost of energy. But you could also put interaction V, which tells you that there is a repulsion between bosons which are at neighboring sites. Now, if you are at half filling and you are doing this in a Mott state, so this is a superfluid state where there is a distribution of boson numbers at every site, and this is of course a random picture. And then if you increase your V and U, then you see that the natural state to go into is that you occupy half the states with bosons because you are at half filling, and this is done in such a way that there are no nearest neighbors. Okay, so this is the proverbial charge density wave state. Of course, charge meaning here its number. So the bosons have pattern. You see that there is a density wave pattern out here. Okay, every site which is the next neighbor of our occupied site is empty, and so on. So, of course, since here you break more than one symmetry, that is in the Mott phase you break translational symmetry, and in the superfluid phase you break U1 symmetry. There is a question regarding the nature of the quantum phase transition in between them, and this is something that people have looked into. But there are experimental ways of doing this, both have problems. What's the problem? The problem, of course, is that here you have to maintain a coherent superposition of two species of atoms, which is experimentally difficult. And here you need to have a way of wrapping up this B, which is the nearest neighbor interaction, and that is also experimentally difficult with most atoms. Okay, so this means that what we have are good theoretical suggestions, but none of them is experimentally very easy to manipulate. Okay, so I don't know why this thing is coming here, but okay, ignore this for the time being. Okay, so the next thing that we know is that so here and in the rest of, for a large part of the rest of this talk, I'm going to discuss a third method for applying for breaking translational symmetry of these bosons, and this is a bit tricky when it comes to the theoretical concept. But the good part about this is that it's absolutely easy to realize experimentally. Okay, it's very easy for the experimentalists to do this. So the idea of this is to create an electric field for these neutral bosons, and of course this cannot be done by an electromagnetic field. That's not possible. But if we think of what happens when we have a DC electric field for a charged particle, we have a linear potential, which is of course unbounded, and that's so the potential is unbounded, but the field is of course a constant. How do we do this? Okay, one possibility is that you see that the bosons typically, this cold atom, this cloud of bosons typically is sitting at the center of a trap. So if you shift the center of the trap, this means that initially you had a harmonic oscillator trap potential, which is like half kx squared for these bosons. Now you have shifted the center of this trap. So you have a potential which is like half k of k times x minus x naught squared, where x naught is the shift that you have put in. And this clearly means that you have a linear potential which is proportional to x naught. Okay, so that I guess is straightforward to see by just simply expanding the this square. Okay, so up to a constant term, which we are not going to be bothered about, this will lead to a term with which is analogous to an electric field. Okay, whose amplitude is proportional to x naught. That is the amount of shift. So that's one way of generating this electric field. Okay, and this is one way that was experimentally taken by Emmanuel Bloch's group in their 2001 experiment that I showed before. And I'm going to discuss the effect of this electric field in subsequent slides. Okay. The other way, which people now use, is to put in a Zeeman magnetic field for this to this atom. So, as I said, these 87 rubidium atoms are essentially in a spin polarized state. So, it's at a F equal to 1 hyperfine state. And once you put in a magnetic field, which is a gradient, which is linear in X, for example, and they know how to create those kind of magnetic fields in the laboratory, you see that this Zeeman term essentially also emulates the effect of a constant electric field for this neutral boson. Because again, there would be a potential, a term in the Hamiltonian which is proportional to X, provided that the magnetic field is linearly growing with X. Okay. Now, this kind of generation of electric field essentially breaks translational symmetry, because now every site sees a different potential, and it has some very interesting effect, and a lot of interesting phases can be realized by this kind of field, which I am now going to discuss. But any question on the experimental way of breaking this, realizing this stuff? Anything which is unclear? Okay, if not, let me move on. So here is the experiment for from Emmanuel Bloch's group in 2001. It's a same paper, the Nature paper that I have sort of alluded to in my previous experimental slides. So, for example, where we were looking into these experiments. Okay, so this is the same group and the same paper. So this is a Nature at 2001, and I'm going to send you these references. Sudipta will circulate it hopefully. So essentially here what they are doing is the following. Just as before, they are creating a optical. Just as before, they are creating a Bose-Einstein condensate out here, and then they ramp up the lattice potential up to a value V0, which is something that they choose. Okay, so if they choose this V0 to be small, for example, 10 times the recoil energy, then of course the system is in the superfluid phase. But if you choose them to be 20 times the recoil energy, for example, you can take the system in the Mach phase. Okay? So that's the role of V0. Now, here, for this period of time, at 20 milliseconds, they put in a perturbing Hamiltonian, and that perturbation is just the electric field term that I talked about. Okay, in the previous, so in this experiment, which was done in 2001, they choose to shift the center of the trap and to create this electric field. Okay, then at the end of this 20 milliseconds, what they do is that they ramp down the optical lattice and hold it to a value which is 9 times the recoil energy. Okay, this out here. What it means is that here the bosons come back to the superfluid state. But the idea is that if you have put in a perturbing potential out here, okay, and if the atoms have absorbed some energy from these perturbations, then when it comes back to the superfluid phase, it's going to be in an excited state and not in the superfluid ground state. The superfluid ground state we know is a central peak which is situated at k equal to 0. However, this excited state is going to lead to a width of this peak and it's going to split. Okay, and this can be calculated, but I'm not going to get into the details of that. But this suggests that the width of this peak is also a measure for the strength of the perturbation. So after holding this here for some time, which is typically 300 microseconds or so, they drop the trap and the lattice and they measure the momentum distribution. So from this momentum distribution, we calculate the width of this central peak, and therefore this width gives you an idea about how much energy the system has absorbed from the perturbation. Okay. So is this part clear? You know, how they measure the width of the peak and why it essentially signifies, you know, absorption of energy from the particle. Is that part okay?
Sir, what is the recoil energy here?
Oh, the recoil energy is essentially, okay, so I should probably get to that. This we did in the last class, but here is the idea. So the recoil energy out here is this basic energy that you can construct out of the length of the lattice, the wavelength of the lattice, and the mass of the bosons. Okay, it's basically h squared k squared by twice m, where k is 2 pi over lambda. Okay,
Okay, sir.
and that recoil energy is the basic unit by which you measure all the energy in the system. Okay, so now you see there's a very interesting effect out here. So if you are in the superfluid phase, when your V0 was 10 recoil energy, you see that with the amplitude, increase in amplitude of this electric field, which is created by shifting this lattice, that is by increasing the shift, you see that as you increase the shift, more and more energy is absorbed, and that's given by the V. And you see that this energy absorption leads to you know, basically phase fluctuations, and these phase fluctuations essentially increases as you increase of the phase fluctuations of the superfluid bosons, and this phase fluctuation increases as you increase the electric field. And if you go to a sufficiently large electric field, then of course the whole system dephases. You are not in the superfluid phase anymore, and then everything plateaus. Okay. However, if you now get into the Mott phase, and let me just come to the last diagram out here, you see that the energy absorption pattern is very, very different. Here, energy is selectively absorbed only if you have a fixed, so 1 or 2 maybe, fixed value of this electric field, as if you are creating a resonance with the system. Okay. So this typically signifies that the system using this electric field can connect from the ground state, which is the Mott insulator here, in the presence of the tilt, to some excited state, which is a very definite quantum state. Okay, and it's at a very definite energy, and it's only when the electric field is equal to the energy difference between the ground state of the Mott insulator and this state, you see this resonance. Okay, and this is what so there seems to be a sharp resonant absorption at fixed electric field amplitude, and which indicates a definite quantum state in the Mott regime. And there was a theoretical question that, you know, what this state is and what the experiment is exactly seeing. Okay, so is this the experimental description clear? You know what they are measuring and everything. Okay, we are going to see a much more definitive measurement later on, which was developed by Marcus Greiner later, around 2011 or so. But let me try to, just based on this, give you a type of theory where you know, we can understand the state here. So this is something that a work that I did long time back with Subish Sachdev and Steve Garvin, and this was sort of this work on tilted optical lattice, trying to explain what they're actually seeing. So imagine the following. Okay, so you have these bosons, and you have put in an electric field, which is given by this T. Okay, so the Hamiltonian is of this parent Mott state, and I have taken 2 bosons per side, but you could take 1 boson per side, and it's the same thing. Really doesn't matter. So essentially, the Hamiltonian is some hopping term plus this electric field and Q. And we are in a regime, and this is interesting because you can be in a regime where this interaction and the electric field are both large compared to the hopping. Okay? And this is a regime you never ever see in a standard condensed matter system because there, if you are to bring in an electric field, which is compatible with the hopping parameter or the bandwidth of the lattice, you are going to have electric breakdown. Okay, that never happens. But here you can reach this limit. And but first, let's look at the situation when I just have the electric field but no interaction potential. Then it's a single site problem. Okay, and this is a quantum problem. It's a quantum mechanics problem because you can just solve for this problem exactly. And this problem is known as the one-year start ladder. Okay? Here, it's a Hamiltonian where bosons can hop from one side to another, and it sees an electric field which gives a linear potential. So on a lattice, this problem is exactly solvable, and the wave functions comes in terms of Bessel function, and the energy is proportional to some n, which is close to this lattice length. But the important point that I want to make is that for a lattice with a single band, okay, this the solution of this problem tells us that all the bosons are completely localized in their respective lattice size. Now, this is very different from the classical physics that you see. If it's a classical physics, you can think this lattice size as buckets and these as balls. And if you tilt the buckets, you would expect that all the balls are going to go and basically aggregate on the last few buckets out here. Okay, so there would be a rundown. Now that happens in a quantum system. Of course it does, and that's called the electric breakdown, where things accelerate. But if you have a single band in a given lattice, this electric breakdown cannot take place. Okay, this is a standard thing, which if you solve this problem using this one-year start ladder analogy, you can see it for yourself. Okay. So this means that what we have is like a metastable state, so that going from this state to anywhere else in the absence of this U, it takes a very, very long time. So although this is not the ground state of the problem, but it's a metastable state from which the atoms do not move much. Okay. So now the question is that what happens when you put an interaction over and above this metastable state? That's what we are going to discuss. But is this part clear? Any questions?
Sir,
Yeah.
since you said about the linear stack ladder, so I have a question actually, because I was reading this thing earlier. So the linear stack states and linear function is the same thing, or is there
No, it's very different. One-year stack ladder, the wave function for the one-year stack ladder are Bessel functions. Okay, one-year functions are also localized wave functions, but they are not solution of this one-year stack ladder.
Okay.
Okay. Any other questions? Anything? Okay, so if not, let me just get into this. So to solve this problem, the idea is that since I have a metastable state, I want to find out that in the limit where this, in this regime, where E and U are both large, but U minus E could be small and W is small, how do we describe this system? So we want to construct an effective Hamiltonian which describes the low energy physics of this system. Now, okay, by the way, this is your one-year start ladder, and these are your wave functions. Okay, these are the Bessel functions. So this is very strongly localized at j equal to a for large G. And this is easy to see because you see for large G, the coefficient of this Bessel function goes to 0, which means only J0 has finite value, which means that the wave function is localized at the mth eigenfunction is localized at site J. When J takes the value n and so on. Okay, so the point is that how do we get out from this state? So the first thing we can do is to see, that suppose I put an extra boson on top of this, what happens? Well, there is this extra boson, and you are putting, since you have put an extra boson out here, it costs you some energy in terms of U and some U. But now this boson needs to move and lower its energy if you have to sort of get the state close to the ground state. And it cannot, because again, the Hamiltonian of this extra boson is just the hopping plus some electric field, which the boson sees as it tries to move on. And that's again a one-year start problem, which tells you that the wave function is localized. So the boson essentially stays localized to these sites, and therefore it can never lower its energy by hopping. And therefore, these quasi-particles and quasi-holes are not close in energy. They are at least order U energy higher compared to the ground state, because that's typically the order of energy that you basically require to put in an extra boson. Similarly with a quasi-hole, if you want to take out one, a similar consideration. So the point is that these are not states which are close to the ground state or the metastable state of these bosons in an electric field. What are close states are essentially some dipoles. These dipoles essentially constitutes a process where you can go from one lattice site to the next. So a boson just hops from one side to the next. Okay? Now this, of course, costs an energy U minus E, because when the boson goes here, it gains an energy E because it moves in the right direction of the electric field, and it loses an energy U because now it has stronger repulsive interaction out here. Okay. So therefore, the total energy cost is U minus E, and when U and E are both large but their difference is small, this state, the state with, let's say, one or many additional hops like this. Okay, so there is a hole on this side and a particle on the other, and this constitutes a dipole. And so a state with many such dipoles is resonantly coupled to the parent mod state. It's very close in energy to the parent mod state in the limit when U and E are similar. Okay. So based on this, we created a model. Okay, and the model is very simple. That it takes, so it's all in terms of these dipoles. So you can create a dipole, and that is going to cost an energy U minus E. Okay. And then because the bosons can hop, okay, a spontaneous hop of a boson out here can create or eliminate a dipole. So you have a term which is like B plus D dagger, which can create and eliminate a dipole. So essentially, this is not a number conserving model, but this model is really simple. And if it was just these two terms, you could solve the model exactly. But this model becomes non-integrable because you have constraints. So what are the constraints? The constraints are that you can only form one dipole on a given link. Okay, because if you try to form two, you find that the energy that it costs to form two dipoles on a given link is way larger than it's not a part of this low energy substrate. It requires way larger energy. Okay, because it would be something like U minus 2E, which is large in energy. And similarly, you cannot construct two dipoles on neighboring sites, because constructing two dipoles means a boson would hop from here and then to here. Okay, and that would mean that it would gain an energy U minus 2E, which is again not a part of this low energy substance, because U and E are all large energy scales and U minus E is small. So any questions on these constraints? Is this clear why the constraints are there?
Sir,
Yeah.
sir, can you also create the second diagram that you saw? That is possible, right? 2 times U minus E.
Oh, sure. You can create as many dipoles as possible, as long as they are not the nearest neighbors. They will correspond to an energy n times U minus U. Sorry, n times U minus E. And that, of course, is allowed, because U minus E is a small quantity. It can go close to
Right. So basically, we cannot create at a particular end. Right. A particular
so the only thing is that, see, here there is a dipole between this link and that link. What you cannot have is a dipole between this link and that link. Okay? There is no common sharing point between two dipoles. That cannot happen. Okay. So, any other questions? Okay, so let's just move on. So now, having the model, let's just analyze what the phases are. So I'm going to be very brief here. So the first thing is that when the electric field is weak, when U is larger than E, you see that this causes a large positive energy, and so the ground state is a ground state of zero dipoles. Okay, which means that all the bosons, the original boson, sitting at the same lattice site and not hopping to the next one. Okay, so that's also typically called the dipole vacuum, because there are no dipoles in that state. Now let me skip that. But the other thing is more interesting. When your E, the electric field, is large compared to E, this means that so this means that when you have this U minus E to be large and negative, you are going to form as many dipoles as possible. That's your ground state. However, you see that you can, if you have formed dipole on a given link L, you cannot form one at L plus 1. So this means, just one second. Yeah, so this means that you can form dipole either on all odd links, 1, 3, 5, 7, 9, etc., or on all even link, which is 2, 4, 6, 8, 10, 12, because two dipoles cannot occupy nearest links. Okay, so therefore you have two degenerate ground state, and the grounds of this model in the limit of large U minus E. So the ground state chooses one of them, and hence it breaks a Z2 symmetry. So the situation here is exactly same as an Ising model, where in the paramagnetic phase there is no symmetry broken, but when it comes to the ferromagnetic phase, it can have all spin up or all spin down. Okay. Now, whatever the ground state chooses, it breaks the Z2 symmetry, because the Hamiltonian has exactly the same energy for all up and all down thing. Okay? The Hamiltonian is just S dot S or SIZ SJZ for Ising model. And so if both the spins are up on neighboring sides or it's down on neighboring sides, it's the same energy. The ground state, of course, chooses one of them. And similarly here, it really doesn't matter whether you create all dipoles on odd links or even links. It has the same energy, but the ground state breaks the Z2. So this behavior is similar to Ising model in a transverse field, a model of statistical mechanics that we know very well. Now, in between, what happens? So it turns out that in between there is a quantum phase transition where the system goes from a dipole vacuum to a maximal dipole state. And the reason why it is a quantum phase transition is that the dipole vacuum state has no broken symmetry, whereas the state with maximum dipole has a broken Z2 symmetry, and two states, two ground states, which are separated, which constitutes breaking of different discrete symmetries, okay, must be separated by a transition. Okay, that's standard thing in statistical mechanics, and so you have a transition, and it's not too surprising that it's going to be Ising-like, okay, or would belong to the Ising universality class. The reason is that we have already seen that the state here is very similar to Ising. It breaks the same symmetry, and its behavior is very similar to Ising model. So what we have realized here is a way to emulate Ising model using this optical lattice. Okay, so that's so you see that the ingredients are so different. You have a lattice of light, you have some tilt in your optical in your trap, or you could have some magnetic field, etc. But the physics, the low energy physics, and the associated properties of the system mimics an Ising model. It's just a change of variables. What you measure is different, but it's really so this tells you that this is another signature that these platforms can lead to emulation of statistical mechanical model once we understand the connection. how to translate from one language to another. So any question on this? So after this, I'm going to go and talk about another experimental realization of this. So anything which is unclear? Okay, if not, let me try to sort of talk about another experiment which was done in Marcus Griner's group in 2011, I think. And I'm going to sort of tell you a bit about these experiments. And for more details, I'm going to send some references which Victor will hopefully sort of send you. Okay. So the idea of this is that in the previous experiments, when we are measuring momentum distribution, that's a very nice thing to measure if you're in a superfluid phase where all the bosons are roughly one momentum state. But it doesn't give you much information in the Mott state where everything is completely delocalized in momentum space, because it just looks like a random distribution of blobs. Okay. So the point is that there are two ways out of this. One of them, which I'm not going to discuss, was suggested long time back, and that was the fluctuation measurement on this momentum distribution of Mott phases, and that essentially told you that what kind of phase you have. But that's one way, and that's not experimentally very easy to do, so I'm not going to get into that. But what these people, Marcus Griner's group, is that they could actually take a picture, which is a single site imaging of these atoms, which was done in a very nice way. So first of all, what they could do is to first prepare the state. So here is the procedure. Sorry. First, they prepared this 2D 87 rubidium atoms, a BEC, a Bose-Einstein condensed of roughly 10 to the power 5 atoms, and it's at F equal to 1, and they used a magnetic trap potential. Okay, so this is their basic system. Now, what they do is that project a square optical lattice on top of this, which means that they have now created, if the optical lattice is large, they will be creating a two-dimensional mount insulator. So they ramp the lattice depth, and they could go to 6 times here, or 10 times here, or 16 times here, or any other such stuff. And depending on what your value of this lattice depth is, you are going to either have a Mott phase or a superfluid phase. So superfluid phase at lows here, and a Mott phase at a large. So after the state is prepared, what they do is that when they have,
So the 2D 87 rubidium, like the tight binding in one direction.
No, this is a 2D experiment. It's tight binding in both directions. This is not the experiment with the electric field yet. I'm just describing the experimental setup in a simpler context. Okay, we're going to come to the electric field in a moment.
Okay, sir.
Okay, it's a 2D system of just 87 rubidium atoms, no electric field. So you have just created a Mott insulator by ramping up your lattice potential. That's all.
Okay, sir.
Okay, but now comes the difference. Here, what they do is that after the state is prepared, they certainly increase the lattice depth to a large amount. So the atoms, after this sudden increase of lattice depth, are essentially frozen to the real space configuration that they had, okay, before this lattice depth was increased. Because if you suddenly increase the lattice depth, what happens is that the atoms cannot really hop. Okay, so that's what. Now comes the next part.
And this lattice depth they are doing, like they are increasing by regulating the wavelength of the laser. Is it correct?
Intensity of the laser light.
Yeah, I know.
Okay, so that's what they do to increase the lattice. So the larger the intensity is, the deeper the lattice potential is. Remember, the potential goes as mod E square.
Yes, sir. Yes.
Okay. So the point is, then what they do is to apply light. in a special frequency, so that this is tuned in such a way that if there are two or any even number of atoms in a trap, okay, then these interact with each other and the light, and they just fly out of the trap. Okay. So the light gives it sufficient amount of energy, provided that there are at least two of them. So there is this is called light assisted collisions. This is atoms collide with each other assisted by light, and then they are ejected out of the trap. So there is a whole history of how this is being done. Okay, the paper I'm going to send you to have the details. But what they do is to have this light assisted collision, and they eject a pair of atoms from the trap. So clearly after that, if you had even number of atoms on every side, you are going to see that your lattice would be empty out there. If you have odd number of atoms at every side, then what we see is that there is at least one atom remaining in the trap, which means that after this light assisted collision, you can measure the parity of occupation of these atoms. So, whatever remains in the trap is the parity of occupation. So it's 1 if it is oddly occupied before this assisted collision, and it's 0 if it is evenly occupied before the collision. Okay. So now what they do is that they image the remaining atoms, and this is done by some fluorescent imaging technique. Okay, so they let the cloud expand, and then they put it on a fluorescent screen, and from this they can basically get the position of the atoms inside the trap. And you see what happens here. The dark spots are the ones which was previously had 2 or even number of atoms, and the even spots are the ones which had odd number of atoms. So in a superfluid phase, it's a random superposition of odd and even sites, whereas in the Mott phase, it's almost so it's almost everything had odd number of occupation. So this is a n equal to 1 Mott state. In their system, it's supposed to be n equal to 1, and this is a superfluid state. So this now distinguishes by optical imaging between superfluid and the Mott state. So essentially what they do is to plot the probability of odd occupation, and for the probability of odd occupation for the Mott state could either be 0 or 1, because if you had a Mott state with n equal to 2, then it's all 0, and if you had a Mott state with n equal to 1 or 3 or things like that, it's all 1. Okay, whereas in superfluid phase, it's a random distribution, and this probability can be estimated from the Poisson distribution. So typically the occupation, the number occupation in the superfluid state follows the Poissonian statistics, and using that you can find that the superfluid would have 0.5, 1 minus exponential average of n, etc. That's the probability of odd occupation. Okay. So these are all verified experimentally, and the details are there in the paper. But now come to doing this with a linearly electric field, and in this experiment, what they did is they put a linearly varying Zeeman field. So this is the second technique for generating a tilt. Okay. So now with this tilt, of course, it's same as what I showed before. They were just looking at, they wanted to describe the whole system in terms of spins. So they just mapped onto spin variables from dipole. So the easiest way to understand is that, if you have a dipole occupation, then it's a spin down. Whereas if you have dipole vacuum, then it's a spin up. So Sz is half or minus half depending on where n is 1 or 0. Okay. And here, of course, creating a dipole means S plus, which is D dagger, and destroying a dipole means S minus, which is D. And if you add those two, you get Sx. If you take the difference of them, you up to a factor of I, you get S1. Okay, so that's a standard mapping. So a Hamiltonian, which was this dipole Hamiltonian, can be mapped in terms of a spin language. And here, this factor J essentially implements the constraint that the number of this thing, the number of dipole on individual side is going to have a very high penalty. This J is a very large number. This dipole model has J tending to infinity. Here they just put J to be a large number. Okay. So essentially, this means that we have realized a spin system on a lattice by using this technique. Okay, so that was the main point of this paper. And and of course here what they found is that they did this single site readout, just as I explained. They can measure the parity of occupation, and they found that they can get into a state where these dipoles have formed, and that would be all empty, non-bright states, whereas they can also get into a state called low electric field. So if the tilt is large, they get this all empty state, and if the tilt is small, they get this all occupied state. And more importantly, they can move from one to another and back. Okay, so they can tune between this paramagnet and antiferromagnet in their language states, maintaining coherence in the system. And if you look at it, so this is their tilt, and as you increase this tilt, you go from, and they plot the probability of probability of sites with odd number of occupation, which goes from close to 1 to close to 0 as you go from a paramagnetic to a antiferromagnetic phase as a function of this electric field. Okay, so the point is that this is this is a much more direct validation of this model that we wrote down. But the point is that more importantly, it gives you a way of realizing an antiferromagnetic state, a symmetry broken state on an optical lattice. For this experiment, they considered a one-dimensional lattice instead of the 2D lattice that I talked about. And the way to do this is that in the transverse direction, the direction transverse to which the tilt is applied, they just ramp up the lattice potentials to a very, very large amount, so that the chains, in a 2D lattice, they don't talk to each other, and effectively it becomes a 1D chain. Okay. So that's how they measure this tilted. That's how they measure things in this tilted optical lattice. So any questions regarding this? Anything which is unclear? Okay, if not, let me try to sort of look at another aspect of this. So in these systems, because this is totally isolated from the environment, one can not only look at the ground state, but one can look at the quantum dynamics. That is, if you put in a perturbation on this tilted Bose-Hubbard lattice by making a parameter time dependent or things like that, you can look at what happens for the dynamics of these quantum systems. Okay, so okay, I'm not going to get into the details of this so much. Okay, but let me try to tell you a little bit about this. So when it comes to non-equilibrium dynamics of quantum systems, the typical model that you study, and this is something, it's a basic quantum mechanics model, is the two-level system. Okay, so you can think of it as two magnetic fields, one in the z direction and one in the x direction for a spin, and the magnetic field in the z direction is made linearly dependent on time. So here are the instantaneous energy levels. So if at sufficiently far in the past, these two levels are very widely separated because of this T, and one is the ground state, but sufficiently far in the future for T going to plus infinity, and back in the past means T going to minus infinity, the ground state and the excited states are swapped. And in between, there is an avoided level crossing whose magnitude is determined by this delta. It turns out that the dynamics of this system can be exactly solved, and the probability. So if you now go through this with a fixed rate, the probability that if you started from state 1, that you will end up in the ground state is an exponentially decaying function of time, and that depends on the rate at which you have taken your system. This tau is inverse of the rate, and there is a strict principle for this called the Landau criterion. And let me explain this a little bit. So you see that at any instant of time, you have an instantaneous eigenvalue difference, which is given by delta of t. So at t equal to 0, this is just delta, but at other points, you have some delta. Now, if your rate is such that this change in this delta of t is greater than delta square, then you form excitations. That is, you take your system from one state to the another. Okay. However, if this is small, you don't form any excitation. Okay. Now, the point about passing through a phase transition, which is there in many body systems, but you can think of this as a two-level system with this delta going to very close to 0, is that near the phase transition, Landau criteria for excitation formation is always satisfied. Another way of saying this is that there is no sense of being adiabatic exactly at the phase transition point, because the energy gap between the ground and the first excited state vanishes. Okay? So you invariably form excitations as you go through a phase transition. Keibel and Zurek essentially estimated this phase transition thing. Okay, so the amount of excitations that you form, and what happens is that for Ising-like model, it turns out that if you are moving the system with a rate tau, tau is inverse of the rate at which you change your energy, the parameter T over tau in the Hamiltonian that you see. Your defect density is going to scale as, defect meaning the excitation density is going to scale as 1 over square root of tau. So as tau tends to infinity, which means if you are moving really, really slowly, you see that this excitation density goes to 0, which is perfectly fine. And if tau tends to 0, you are going to form lots of excitation. Of course, the theory doesn't work there because this is only for slow dynamics. Sorry, this camera is going to create a bit of problem. Okay, so now, so let me skip this. So this behavior is typically called the Keibel-Zurek law. Okay, so it tells you that the density of excitation goes as some power law with the rate at which you are taking the system through the transition. And it also tells you, and I haven't shown you these details, but it tells you that for a generic quantum phase transition, which is characterized by these exponents, nu and z, u being the correlation length exponent and z being the dynamical critical exponent, and d here is the dimension. It's a universal number. Okay, this power law, the power of this power law is a universal number, and this has been proved for several systems, and many people have worked on this, starting from Keibel and Zurek, of course. But the point is that what I wanted to tell you is that now that we know that here in the experimental system, we can vary this tilt or the electric field to go from a paramagnetic to a antiferromagnetic phase, which is separated by an Ising transition. We can try to find out what the Keibel-Zurek law is. And what we find when you look into this Keibel-Zurek law for this kind of systems is that, so what we find is the excitation, something analogous to excitation density. And we find that indeed that these exact numerics that one sees essentially seems to point that you are going to see this square root of v. V is just 1 over tau, which is the rate at which you are, which is analogous to, which is exactly as the Keibel-Zurek result predict. So this is another thing about these ultracold atoms, that this gives you perfect platforms for verifying some predictions about dynamics around quantum critical points. Okay, so I don't want to get into the details of this because it's going to take us in a different direction. Okay, but what I'm going to tell you is that this is not the only possible So this is not the only possible type of symmetry broken state that we can come up with. There are others which realizes transitions in other universality class, and there are also this kind of considerations of asking the question that what would be your excitation density as you vary this electric field or whatever parameters that you vary in this ultracold system through the transition. That can be answered. And essentially, one such state is called the, so another state that comes in here is that you can have a repulsive, so you can generalize this. So remember when we looked at these dipoles, we found out that these dipoles have a constraint that you cannot have two dipoles on neighboring sides. So now you can think of generalizing. So you can say that, well, instead of having a constant between two neighboring sides, I can have a constant between three neighboring sides. And that's going to give me a state like this, where you can put only one dipole for every three sides when the electric field is large. And that means you have, instead of a Z2, you have a Z3 broken symmetry. Okay. And what we looked into this sometimes back, and we found that this essentially satisfies. So there is also a critical point separating the dipole vacuum and this symmetry broken state, and that belongs to the three-state quartz universality class. So these are also things which has been realized in optical lattices. Okay, and one can similarly do dynamics with this kind of stuff, and there is an expectation in terms of this excitation density once again for this Weyl thing, which I'm not going to get into the details of, but there are some definite predictions. Okay. But the bottom line of all this is that using these techniques of this electric field and another experimental system called Rydberg atoms, which I'm going to come in the next class, the last lecture, you can emulate, symmetry broken states in optical lattices. So there are two advantages of this. First is that it gives us very interesting connections between different systems made out of different degrees of freedom. So for example, if I think of these bosons, what are the degrees of freedom? The bosons, the atoms are one. The optical light, the laser, that's another. Okay. And on top of that, you have the trap and other things, which are the generic microscopic degrees of freedom. But when you put all of this together, you come up with a many-body system, the low energy physics of which can be described in terms of spins, okay, or dipoles, which are not directly linked to these bosons. Okay, so the bosons are neither the spins nor are the dipoles. There are some very complicated connection between the bosons and the dipoles. Yet, in this dipole or spin degrees of freedom, it's much easier to describe the basic physics of the system. Now, this phenomenon, where the degrees of freedom which leads to a simple description of the low energy physics being completely different from the microscopic degrees of freedom, is an example of a phenomenon we call emergence. So it turns out that the low energy degrees of freedom, low energy physics of a system can be described in terms of some completely different degrees of freedom, which is not simply related to the microscopic ones. And the microscopic ones, they lead to a very complicated description of the low energy degrees, and that's not the way to look at this system. So this tells you that there are emergent, simpler degrees of freedom at low enough energies. And this phenomenon goes by the name of emergence, and it has now permeated into different fields of condensed matter. In fact, this is the basic way of understanding, how strongly interacting condensed matter systems works. So that's point number one. Point number two is that the beauty of this optical lattice system is that it's all separated out from the environment. And as a result, we can study its dynamics. So what happens when you take a system in a laboratory and you try to probe it by perturbing stuff? Of course, the system is quantum, and therefore you should see quantum dynamics. But the system almost immediately dephases, and the reason for that is that it's very strongly connected to the environment, whatever else is there in the lab. But this kind of systems You see, what happens is that they are isolated from their surroundings to a great degree because the temperature is so low, and therefore it's not at all connected to anything which you can call environment, and hence they are perfect platforms for studying quantum dynamics. So these two features, essentially, and on top of that you have control, because everything is controlled by tweaking laser lights, and the experimentalists know how to do this very well. So essentially these two things overall leads us to believe that this could go as good emulators of quantum models, which has been theoretically studied for long. Okay. So I think it's almost time. So I think okay. So so I have these Rydberg atoms, but I think I'm going to take this up in the next class because it's a whole new subject. So let me stop here.